Okay, I think it's time. Is it time? Do we have any announcements?
Yeah, just that labs are starting this Friday, and then we'll go on next week. And I'll be holding discussion tomorrow, but not next Wednesday. So next Wednesday, it'll just be lab time. And we're going to post homework 7 soon, today. So watch out for that. But the next homework is due on Thursday. Yeah, that's it.
Okay, thank you. And the lab should be pretty cool because a lot of the things that you've seen so far in simulation, you'll be able to actually run on an actual scanner and see those effects. So even though it's going to be remotely, I'm sorry, but you're still going to be controlling spins, that are located somewhere, and not just simulating them, which is definitely, an advantage. And this scanner doesn't really make a sound, so it doesn't, that experience is not, you won't appreciate it as much as, going to a full body scanner. Okie doke. Let's see. So you noticed that there was no song today and no art, because I'm planning to play something during the lecture. If we get there, I don't know. I always plan something, but then I talk and 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 I don't get anywhere. Okie doke. Let's see. I'm also noticing I'm developing a very strong accent again, right, Anita? I didn't hear your comment, but and I didn't see your face because I was switching. But, I'm sure it was interesting.
You sound like a foreigner.
Thank you. I'll take that as a compliment. Since I am a foreigner. All right. So last, what?
Yeah, I was gonna say, enjoy your accent, Mickey.
Oh, I recognize a similar accent over there too.
No way.
All right. Where were we? I think we talked about spectral pulses. So slice selective pulses, you can kind of understand in the sense that we put a gradient, so spins resonate at different position will resonate at different frequencies. Right. I could speak with the French accent now with my hat. Yeah, it's cold because I got a haircut, so I'm putting a hat right now because it's a little bit warmer that way. At least I don't look like a cat, and I don't appear in court as some lawyer did in the past. All right, so if you think about a spatial pulse, right, like a slice selective pulse, you apply a gradient. That means that spin, resonate different frequencies in a linear distribution across space. And then we apply a frequency selective RF pulse. And because we're applying a frequency selective RF pulse, only those spins within the bandwidth of the RF pulse will be excited. And we gave kind of an explanation through excitation K-space and all that stuff. But that concept is, I think, should be clear to you by now. But you can also think of chemical shift as a different resonances. Let's say you have a, so if you apply a gradient, you create effectively off resonance spins, spins outside of the center will resonate at different frequencies, and those would vary linear in space. So they resonate at different frequencies, but so the gradients create this, I guess, inhomogeneity. At the same time, this inhomogeneity in resonance can come from other reasons. It can come from, for example, from chemical shift. Different species may have different frequencies, right? So they could be inside the magnet, but they resonate at a different frequency because they have a certain chemical, they're bound differently to a molecular structure, so that changes their resonance frequency. So in some way, we can think of off resonance as so we can think of gradients as a source of off resonance, but the source of resonance can be something different. So then, in that sense, spins that, let's say, if you apply a gradient and spins that are away from the center, will start the accruing phase, right? After we excite them, or like as they create a transverse magnetization, they'll start accruing phase because they resonate at a different frequency. Now, thinking about this, in the same analogy, you can think, okay, so in that case, if I have an RF that is applied like a sync pulse, but the gradient is off. If the gradient was on during this RF, then I can think of this situation. So spins at a particular Z position will precess at some frequency, gamma over 2 pi GZ times Z, right? They'll precess at this frequency. And so there will be associated K-space with this, as time goes by, they'll accrue phase. And so we then derived K-space. So Kz of T times Z will be the integral from time T to time capital T to the end of the pulse. Gamma over 2 pi GZ, right? dt, and of course times Z, because I multiplied here by Z. So this is pretty much, I guess, the phase increment, I guess, that you get, because you're at a different position. Okay, so now the question is, what about chemical shift? Well, with chemical shift, spins will precess at some off resonance frequency, let's say some delta F. The reason for it is not because of a gradient, it's because they actually have a different frequency. So those spins, what's the difference really from a physical point of view? If a spin precesses at delta F, or I take another spin that precesses, that naturally is on, right, like a spin that's supposed to resonate at Lamour frequency, but because I put it away from the center of the magnet and I put a gradient, then it precesses at a different frequency. There's really, from a physical point of view, no difference whatsoever between these two, right? They both precess at exactly the same frequency. One because of off resonance, because of chemical shift. The other one because it's it's far away along Z, and you put a gradient on. So we can develop a K-space interpretation of, or excitation K-space, or even readout K-space, by the way, in the same way that we did it for when the gradient is on. We can interpret it in the direction of the chemical shift, in the dimension of the chemical shift. So in that case, spin will precess at an offset frequency, delta F. So then you could develop a K-space, which is, K delta F. K-space of delta F is a function of time times delta F, like we did here. Well, what is this K-space? Well, this K-space is really the integral from T to T, capital T, of constant, right? There's no Z position, there's nothing, times delta F. So really time, the time that it's left till the end of the pulse is our K-space for chemical shift. This is a little bit weird to think about it, that time is in fact the spatial frequency of chemical shift, which is off resonance frequency. It's a little bit, awkward to think about it. But in fact, time is really the scale k delta f, because the effect of this precession is exactly the same as off resonance. So then, effectively, the content of the spectrum of the RF pulse will affect our selectivity of chemical shift in the chemical shift dimension. And then I showed you this thing. Well, okay, well, if I apply this RF, and RF, it's like this is time, but this is also the dimension of, delta, k delta f, I guess. And in that case, how does, actually, I didn't do it here, but how does time evolve, right? Well, if you integrate t to t, well, if this is the end of the pulse, then our k delta f looks like this, right? So in that case, we start at some positive k delta f, and then we deposit a sink, and this point over here is k delta f equals 0, and that is, of course, at time t, capital T. That is 0. And so if we want to figure out what is our selectivity in the chemical shift, then we need to take the Fourier transform of this thing. And what is the Fourier transform of this thing? It's some rect in the frequency, right, in the chemical shift. So this is our k delta f, and we compute the Fourier transform. And what will happen is that we'll have some rect that is going to be around omega 0, right, our resonance frequency. And then it will select some chemical shift around the water frequency or around proton frequency. But if we choose it appropriately, such that this bandwidth is limited based on, whatever the sink that we apply and how long it is, then if we actually look, let's say, at the lipid frequency, lipids have a resonance frequency that is different than free water. Lipids at 3 Tesla resonate at a frequency that is 460, about approximately 460 hertz below the resonance frequency of water. So if this bandwidth over here is around water, then we will not excite lipids. We will excite only water, and we will not excite lipids. This is extremely powerful, because I showed you before that there are some situations that the lipid signal can obscure edema, right? I showed you with the finger example in I think the first lecture or the second lecture or so. And if we are not exciting the lipids, then we will be able to see. For breast imaging, the breast tissue is full of fat. Obviously, you know that. Tumors are actually not fatty. And so what happens is often you'd like to inject, for example, contrast agent to look at breast cancer. You inject the contrast agent, and that contrast agent goes to the tumor, and you'd like to image it. But because of all this fat around it, fat is really, really bright on T1, and contrast is often also bright on T1. So it's really, they're really competing with each other. So if you can actually just excite water, then you'll be able to see the tumor better, as opposed to having the fat. So it's extremely, extremely useful. Okay, so effectively having some pulse that is long in time will have some spectral selectivity. That means that if we want to do slice select that excites everything, we have to make it very short. Otherwise, it will also be somewhat frequency selective as well. Okay, so we have to be aware of that. Now, k-space of chemical shift, which is time, always moves. This gradient time is kind of like a gradient of chemical shift, if you think about it. It's always on. Hence, we can never center the K-space, excitation K-space, because we always end at the end. We cannot go back and refocus because we cannot apply reverse time like we apply reverse gradient. Okay, you have to understand that as well. Okay, so in that case, the Fourier transform of this will have a phase, right? A linear phase across the excited spin. So no phase at the center, but linear phase increasing and decreasing on the other side. So there is some phase associated with it. It's not going to be excited with exactly the same phase. You also have to understand that. Okay, so now the question is, what about this situation where I apply, these impulse RF that have an envelope of a sink? You can then think about it as, oh, I'm applying an RF and then it's multiplied by an impulse strain. What is the Fourier transform of a sink multiplied by an impulse strain? You have to unmute if you want to say something.
A repeated Rex.
Yes, a repeated Rex, that's right. So, whoa. Oh yeah, I need to draw this. I didn't prepare it. So in that case, you will have, one rect here, and then one rect here, and then one rect here in chemical shift. And their distance is going to be inversely proportional to the distance of these. Let me just use a different color so you can see. The distance between these are going to be inversely proportional, right? In the same way. Okay, so this is going to be repeating. Now, the situation may not be a problem because normally you'll have some frequencies around water frequency with natural off resonance because of magnetic field homogeneity. You may have fat, lipids over here, but really there's no spins anywhere else. So really the fact that you're putting energy in these frequencies doesn't mean it's necessarily going to excite anything unless there is something there, Okay. All right. So here comes the situation where we're going to use the fact that if we apply pulses over time, we're selective in the chemical shift. If we apply also pulses with a gradient, we're selective in space. And create a pulse that is selective both in space and frequency to our desired criteria. And then that will allow us to create what's called a spectral spatial pulse that will, for example, be able to excite only water and a slice. Here, it excites the entire volume, but only selects water. Previously, when we did, you know what, I don't know where it is. When we did slice select, we excite all the spins, all the chemical shifts, but we excited the slice. Now we would like to excite certain chemical shifts, for example, just water, in a particular slice. So both at the same time. And that's one of the coolest thing that you can, and this is all came from the notion of excitation K-space. That's what led to it, to this development. Okay, and it was developed by Craig Meyer, who's now a faculty in University of Virginia. But he was also a student of Al Makovsky and in my former lab, MRSRL at Stanford. So you see a lot of people came out of this lab and spread out to the entire world, and pretty much, it's like helo cells, it just took over the entire population. Everybody knows what helo cells are? If not, there's an excellent book, The Story of Henrietta Lacks. I think that's the book, and it's a fascinating story about I guess abuse of privacy, as well as huge contribution to science, and and anyway, it's a fascinating story, so I highly recommend it. Moving on, changing topic. All right, so what we're going to do is we're going to look at this pulse where we have an envelope, right? And we put these impulses, okay? That would create a repetitive pattern in chemical shift. No slice selectivity. However, what I'm going to do now is I'm going to replace those impulses with sinks. My coordination. Have you ever tried to draw a sink upside down? Try that. Not easy the first time. All right. And then I'm going to put another sink around this. And then another sink around this, and another sink around this. And now I got it. Another sink around this. This is still frequency selective, right? Now, what is the frequency selectivity? Is really repetitive, but you can also think of it as being convolved. So it's like it's an envelope of a sink multiplied by a delta train and then convolved by a small sink. So what is the result in the frequency domain? That your repetition are going to be, tapered, because by a wide, rect, right? They're going to be, you're going to have repetition, but they're not going to go to infinity in the frequency domain. They're going to cut off because of this sink. Okay. All right. But we're going to assume that this cutoff, covers a huge amount. That's really what's going to be, right? So, okay. All right. So it really doesn't affect this selectivity. Can you hear me? Okay. Thank you. Thanks for responding. That definitely means that you're hearing me. Now here's the trick. This is still just spectrally selective. Selecting in the chemical shift. Now I'm going to add a gradient like this around each one of those blips, these pulses. Now, what does this mean, the photo gradient here? Well, that means that this one is only going to be slice selective. And this one is going to be slice selective. And this one is going to be slice selective. And this one is going to be slice selective. And all of them are going to be slice selective. And the actual result of this is what's called a 2D pulse. And the beauty about it is that it excites both in Z, this is the Z direction, and this is spectral frequency, chemical shift. And it will excite these blobs in this two-dimensional space. This is Z, and this is spatial frequency. So if this is the water frequency, if this is water, and let's say this is lipids, then I will be able to excite a slice around Z equals 0, only around water frequencies, but will not excite fat. Now it might excite those spins, but fortunately they don't exist, because typically we don't have any spins resonating in those frequencies. Right? There isn't in the body any spins that resonates necessarily there. And if they are, then we will actually excite them too. Okay. So this is a spectral spatial pulse. It leverages time, and usually these are relatively long. Right? If you want to excite, let's say, a bandwidth in frequency of about, let's say, I don't know, 100 hertz, then the length of this needs to be inversely proportional. So how long it should be to produce 100 hertz? It should be at least 10 milliseconds. It should be relatively long, because it's always inversely proportional to the bandwidth. So if you want a narrow bandwidth in the frequency domain, then you need to have a very long pulse. And unfortunately, we cannot speed up time like we can apply a larger gradient. So really, we have to wait, because time is time. It passes at 1 second per second, you know? Except if you're accelerating, I guess, in some, you know, ridiculous speed, close to the speed of light, maybe. But I think it's very difficult to do that in an MRI. So we're stuck with that. Now here's one of the, this is the original paper, Simultaneous Spatial and Selective Excitation by Craig Meyer. And in this case, you see that you have, I mean, the way I applied this, I applied these blips and I separated them, but you can also think of them being combined, you know, being close to each other. You know, let's say I move this to here and I overlap this lobe with this one, so it ends up being kind of like oscillatory. Okay, I separated it to make it easier, you know, for visualization. So the original paper describes an oscillating gradient while applying an RF pulse with an envelope of a time bandwidth. What's the time bandwidth of the envelope? What's the time bandwidth of the envelope? 2. How many zero crossings? Right? Just 2, one here and one here. Otherwise, we would have seen negative lobes, right? And then what's the time bandwidth selectivity of the in space? In this case, also 2, because there's no, like, it doesn't look like a sink. It looks like just a lobe of a sink. So these are just time bandwidth 2, okay? So in the presence of this oscillating gradient, we apply these, you know, time bandwidth 2 RF pulses, many of them. And then each one of them is weighted by a time bandwidth 2 window.
Hey, Mickey,
Okay, and yeah.
why turn on the GZ gradient ahead of the RF?
No, it's not. I mean, there's just probably small ones here. I think, at least. Yeah, or it might be like there's no reason, right? There's no reason to apply it before. Actually, this might have been. You might not be able to see it, but it might have been a minimum phase pulse. So minimum phase pulse has actually an envelope like that. So that might be actually the case. So maybe, but it's hard to see what's going on there. So I don't know. But here's example from the paper where they excite. This is an abdomen scan, and these are the kidneys, for example. Okay, these are the kidneys. Kidneys are usually surrounded with fat. And here you don't see any fat. And this is the abdomen, and there's no subcutaneous fat over here because we just excited water. But then we could say, oh, you know what? How about we center our excitation around fat and just excite fat separately? And this is an example of just fat. And you can kind of see how the kidneys are nicely embedded in fat. Oh, and all this belly fat. Oh, that's great. Oh, and you can grab the nice, you know, fat in the back here. See, lots of subcutaneous fat. So I usually, you know, just if I decide to do a diet or so, I go to the scanner, run a few fat suppression pulses, and I hope that I lose weight by that. But I don't. I don't know why. Maybe the fact that I'm not moving and the fact that, you know, it's just like counter, you know, count each other. Anyway, I'll move on. Here's another example. This is actually a paper that Peter Larson and I wrote a while back. This is actually related to carbon-13 imaging, where in carbon-13, we are trying to image metabolites. And in this case, we wanted to image pyruvate, alanine, and lactate. And the way this works is that you inject pyruvate into a subject, and in the body, the pyruvate converts into alanine and lactate, and also pyruvate hydrate. but it converts to it. So there's a very strong signal. I mean, because we inject pyruvate, there's a very strong signal from pyruvate. And with hyperpolarized copper 13, there's a process where you externally polarize the sample to almost 100%, and then you inject it, and then the signal decays. You have only about 45 seconds before the signal goes back to equilibrium, which is abysmally small. It's really, really tiny. So one of the things that we wanted to do is to be able to image alanine and lactate that are generated from the pyruvate. But if you excite pyruvate completely with a 90-degree pulse, you're going to finish it. Like there's nothing left. All the pyruvate is going to be excited and it's going to die, and you're not going to be able to see anything. So what we want is we want to excite a pulse that excites 90 degrees for alanine and lactate, which have different frequencies than pyruvate. Each one of them also different frequency. And then we all want to only excite 5 degrees pyruvate, only 5 degrees flip angle. So the idea is to do something like this, is to excite at this frequency where pyruvate is, we want to excite 5 degrees. And we want to excite almost maximum for the alanine and lactate. And so that was the design criteria. And so, of course, you see those gradients that are oscillating, right, in the GZ direction. And then this is the RF pulse that we came up with, that its Fourier transform kind of looks like this. Okay. It's Fourier, the spectral Fourier transform looks like this. And then in the frequency and space, you can see the selectivity. This is the spatial selectivity. And this is the frequency selectivity of alanine. This is the frequency selectivity of lactate. And there's actually a very tiny here. It's very dark. It's very hard to see because it's only 5 degrees. Excitation of pyruvate. Now somebody may ask, oh, but you're exciting all this, all this stuff too, right? What about that? Well, we don't care. This is area that we don't care because there are no frequencies there. There are no spins over there, so we don't care. So from a design point of view, this was a filter design where our criteria for the filter design was the following. We said we want to have a ripple of maybe 5% around the pyruvate frequency, a ripple of 5% around the alanine frequency, a ripple of 5% around the lactate frequency, and then don't care regions that, I don't care what's going to be there, but really try to get the frequency to match only in the pyruvate and alanine, and this is the pulse that we came up with. Okay, using just filter design and convex optimization. And this is what we came up with. It's pretty cool, I think. So spectral spaces pulses are extremely powerful. So now the question, what happens at larger flip angles? We only talked about small flip angles. We didn't talk about large. We didn't talk about 90 degree and 180 and like all the analysis of excitation cases we did, for small flip angles. So for large flip angles, there's actually many methods. Either you do a numerical optimization because it's nonlinear problem to design a slice selective large flip angle. It's a nonlinear problem. The other one is optimal control. You can think of, right, like we posed the problem as a linear dynamic system. So, I mean, it's a control problem. So you can use optimal control in order to do that. And people have done that. In particular, Steve Conley, for those who are familiar with, is a faculty in BioE, as well as has an appointment in X. So he developed that at the late 80s. There is what's called the Shinar-LaRue algorithm, which is developed by John Pauly during his PhD. And then there's also perturbation theory. Perturbation theory means that you start with some pulse that looks like, that you do a linear design, let's say a Fourier transform for small flip angle. And then compute the result for large flip angle, and you look at the error and then you try to compensate for that error, and then you just iterate. You can think of it kind of like a back propagation, or a gradient descent, or something like that, to come up with the RF pulse that would result in the desired. But since it's a non-convex problem, that you may not converge to the best solution. Okay, so optimal control is this control problem, and then of course you can control the gradient, you can control the B1, and then you can kind of find what are the gradient and the B1 that will move your spins to the right positions. Okay. Now the Shinnar-LaRue algorithm that John Pauly devised is based on what's called the hard pulse approximation. So even though you're applying a continuous RF pulse with a continuous gradient, you can approximate this by a series of hard pulses followed by gradient pulses. Hard pulse, gradient, hard pulse, gradient, hard pulse, gradient, that they don't overlap. Okay? When you do this, I mean, and you can approximate this almost as close as possible if you just decide to discretize it, to infimum, to the smallest part. Now, this description turns out good things happen, and that allows you to actually do a small flip angle design and then come up with a transformation that takes it into a large flip design. If you're interested to know about this, this could be an excellent project to to implement the Shinnar-LaRue algorithm. Even though it's implemented, many places, if you have your own implementation of that, that would be, that could be, for example, a project, and maybe you can extend upon it somehow. Okay. So that's a possibility. So now let me just show a few things before we move on to the next chapter. Here's a time bandwidth 4, 10-degree flip angle, and slice 10 millimeter with duration 2 milliseconds. Okay, so this is the RF pulse. It's time bandwidth 4, and that's the gradient that would produce an MXY that kind of looks like that. Okay, this is the magnitude, and you can kind of see that this is 1 centimeter. Okay, or 10 millimeter width. Can you see? Okay. And you can also see, because this is a very small flip, that the MZ component really didn't change much, so the approximation is very good. All right. So now I'm going to make changes. I'm going to switch to a time bandwidth 8. If I switch to a time bandwidth 8 and keep the rest the same, then what happens? So time bandwidth 8. So what I need to do is I need to double the amplitude of the gradients in order to keep the slice the same, right? Because I increased the time bandwidth, I kept the time the same, so the bandwidth increased. In order to keep the slice thickness the same, I need to increase the gradient by a factor of 2. So from here to here, I doubled the gradient and I doubled the time bandwidth. And that results in, again, a slice selective, which is 1 centimeter. But it's more selective than before. Here's the difference. You see how it's more selective? It's nice, right? Okay. So now I'm going to change another parameter. Now I want the slice to be 5 millimeter, not 10 millimeter. What do I need to do in order to make the slice 5 millimeter? Same time bandwidth, same everything. What do I need to do? How do I half the slice width?
You can change the gradient.
Yes. To what? That's kind of a question.
Yeah. I think you need to double it.
Double it.
Oh.
Yeah. So if I double, look, I double. You see, it's doubled. Now The slice thickness is 5 millimeter. Okay. And then of course, look at the difference. Also, the refocusing part needs to, I mean, it saturates at some point. So, you know, basically it lengthens the whole thing. Because now my refocusing part needs to be a little bit longer. Because it's already maxed. It's already maxed here. Then if I double this and this needs to be half the area of that, then this becomes longer. Okay. All right. So now I'm going to increase the flip angle to 45 degrees. So look at the difference. Increasing to 45 degrees, well, the amplitude increases of the sink. Okay, that's linear. But then, first of all, now, because 45 degrees, now, you know, cosine of 45 degrees is not 1. So obviously now, MZ component changes, right? The slice selectivity is actually not bad, but we start seeing an increase in sidebands. The sidebands are not exactly as we designed them to be using Fourier transform, because we're starting to violate this Fourier transform assumption. Okay, so the side lobes are increasing, and we also start seeing some MXY component being generated even though it's not supposed to, right? Because we refocus everything, right? So MXY should not be generated, but it is generated. Okay. Now what happens now? I think I'm gonna go to 90. Yeah, I'm gonna go to 90. So when I go to 90 again, this increases. I have to say it's still pretty selective, but the side lobes, you know, are not nice. You know, the side lobes are now much more bigger. MZ now actually goes to 0, so it's definitely not 1, right? Because it's 90 degrees. And then now the MX component is quite more significant. So obviously there's a nonlinear, like it's like, you know, it's not exactly what we want. And so we have to do something in order to make it look like what we want, right? So we have to do SLR, you know, some transform or something to change the poles to, we cannot just use a sink or windowed sink for a 90 degree. What happened when we do a 180 degree? I mean, that's definitely nonlinear, right? Like, you know, 180, completely nonlinear. What do you expect when you do a slice selective 180? Well, you should expect MZ to be slice selective. And what about MXY when you do a 180? You're supposed to not have any component, but because we have transition between, you know, there's a transition band between being positive in MZ and negative in MZ, well, there has to be some MXY component in the transition band. So this is exactly what you'll see now. We increase the pulse, so it's 180. And we see, by the way, that at the center of the magnet, it's perfect 180. It is somewhat selective, but we have a lots of ripple. You know, it's not really a nice, you know, MZ, right? It's not nice, but it does something. And there's, of course, an MX and MY component, but it's hard to see. But really, if we look at the MXY, I mean, we're supposed to see bands over here, but they're really bad. I mean, they're excited too much. So really, this is not a good solution. Now, this is a 180 that was designed with a small tip. So I designed a small tip and then I just increased it to 180. Look what is the difference if I actually design an SLR pulse that does a 180. Look at the difference. That's here to here, here to here, here, here. In this case, look at, oh, this is one of the nicest MZ looking slice selection I've ever seen. Of course, we will get some MXY because when MZ is excited, I mean, the transition width, this part, has to go through MXY. So of course we'll have these bands on the sides, okay? There's no way, I mean, if you go from 0, if you go from MZ up to MZ down, it has to go through here. So it has to excite some MXY. Okay, so we see MXY, but look at this is gorgeous, right? So the difference is actually very interesting. Hold on. Is that, first of all, it looks like a sink, but it's not a sink. It's actually more narrow, and it actually has a little bit of a higher bandwidth. But and here are these two next to each other. This is a small flip angle that increased it all the way to 180, and so it's not very selective. This is the SLR 180. You see, it's more narrow. It still kind of looks like a sink, but not exactly. It's just more, slightly different. And that difference makes the whole difference in the selectivity. The last thing I want to show you is these, frequency selective RF pulses. So here's an RF with a gradient, RF with a gradient, RF with a gradient. And then you could see that there's an envelope, right, of time with 2 over time. And what I'm showing you here is if we first just apply the first pulse, it will excite water and lipids pretty much in the same way, because this is just regular slice selection without frequency selection. Now we apply the second pulse. Now you start seeing some frequency selectivity, still slice selectivity, but there is some frequency selectivity. And after the third one, look at how the lipids are going to be nulled and water is going to be excited. Okay. So hopefully that, puts a nice kind of summary to what we covered. Okay. All right. Stretch for 2 minutes. We're going to move to a different topic. So you have to focus. And it's important that we actually cover this because we need that for the lab. Okay. So there are certain concepts that we need to cover, like T2 in imaging, T2 star, which we haven't spoken about, and then spin echoes in order to do the lab very well. So hopefully we'll be able to do this. If not, then I'll just have to go a little bit quicker on Thursday. Oh, we're going faster in the speed of light, so time to move faster than 2 minutes. 2 minutes ended up already. In 15 seconds, they ended up these 2 minutes. So now we can move on. Okay, stretch. Okay, now we're talking about chapter 7 in imaging consideration. Please read those imaging consideration. It's very important, by the way, for the lab. Please read it. I mean, if I'm not able to cover it, if you read it, then you understand what we're talking about. If you don't read it and I don't cover it, you'll just go to the lab and go, oh, okay. But we have to do the lab, otherwise we're running out of time. So it's kind of my fault, but I'm just gonna move my fault into you and just have you, oh, you didn't read the chapter. It's all in the chapter. It's your fault. Okay. This is the beauty about being faculty. You can change the rules. This is why you should get the PhD and then apply for academic positions. Okay. Okay. So next thing that we're going to talk about are practical issues in MRI. So we're going to talk about, look, I have to say, by now, you know a lot. You know K-space, you know excitation, excitation K-space, you know now a lot about MRI. You've in homework, you design a pulse sequence, you simulated it, you got this beautiful principles of MRI image, I hope. And you know a lot. After this chapter, you know a significant portion of the area, and you'll be able to read a lot of papers and understand what people are talking about after we finish this chapter. And this is imaging considerations. Okay. So we're going to talk about T2 decay. We know what T2 decay is, but we don't know what the effect of T2 decay on imaging. By the way, in the homework, you'll have a question about T2 decay in excitation and how to do this analysis. And I believe Ekin is going to go over it tomorrow, that problem. So we gave you in the homework, but then we decided also to go over it in the section. So, old age, I'm getting soft, Okay, so what we're going to do there is we're going to try to analyze what's going on here. So what we're going to do is the spins decay while you collecting the image, right? And so we're going to try to map this T2 decay into K-space, and that will result in some artifacts that would result in some image weighting, which often is desired because we want the T2 contrast, right? But also in blurring in some of the directions, but not all directions. And it's going to be space-dependent blurring because not all tissue have exactly the same T2. So some tissues are going to be blurred and some tissues are not going to be blurred so much. Okay, so it's very interesting. After we finish talking about T2 decay, we're going to talk about off resonance. What happens when you have inhomogeneous field in the magnet? How does this affect imaging? And this is a very important topic. Very important topic. Ekin, how important is it?
Very important.
Yeah.
The most.
Well, don't go.
Maybe
don't
not the okay.
Just very.
Okay.
Very important. Very important topic. Anita, how important is? You don't know. Okay, fine. Fair enough. I'm telling you, it's very important. Okay. So let's try to understand what's going on with this T2. Okay. I'll tell you a story about T2 some other time, but turns out the NMR field, nuclear magnetic resonance, which is kind of the ancestor, grandparent of MRI, magnetic resonance imaging. They have also a T2, which represent exactly the same thing, but they also have another T1 and T2 that is different. And they don't get confused, and I don't know why they picked T1 and T2 for two things, and everybody knows what they're talking about. It's like, I have no idea. It's crazy. But I think there's also words in English that sounds the same, but you know from the context what they are. Maybe that's the issue. I'll tell you when we get there. Right now, I'm in a hurry. Okay, so we look at this, right? We derive this. This is the situation, okay? We apply an RF in the presence of a gradient that does slice selection. Now, you know what this thing does. It refocuses, right? So we can actually do the imaging. Without this, nothing works. And then we have a 2DFT, spin warp, Cartesian acquisition after that. Okay, but here's the issue. So we're going to make a very small approximation. It's a very good one, by the way. We're going to say that the MXY component for that slice is going to be created in the middle of the RF pulse. Even though it's created throughout it, but we're going to say, you know what? The MXY is going to be created exactly in the middle. I mean, it's if you actually simulate, you can kind of see that most of the MXY is created that way. And then the rest is just making the slice look nicer. You know, putting spins that were excited, you know, but they weren't supposed to back up and, you know, spins, you know, that were a little bit ripple, you know, it's but that's what it does. So it really is excited in the middle. So it's a really good approximation. Once it is created, it starts decaying immediately with T2. Okay. Once it is created, it starts decaying. Okay. So the signal starts at a certain level and then it decays. Look how long it takes for us to image. By the time that we get to do the imaging, I mean, our signal is going to be weighted by that decay. Does that make sense? Okay. So the signal decays along the k-space trajectory. So our signal is the integral over space of mxy. It's distributed over space and at time 0, right? And then, you know, we have this k-space that we derived, and we also derived this before, but we ignored it. We said, you know, we can ignore it, right? But right now, we're not going to ignore it anymore. So what we're going to try to do is we're going to try to map this decay into where it is in k-space. Now, k-space is a function of time. This is time. So we can express time as a function of k-space too, right? We can just go backwards. If k-space is a function of time, time is also a function of k-space, right? Because back and forth. So we're going to try to map this decay to k-space and do some analysis on it and see kind of what's going on. Okay. So we excite, and then what is the trajectory of k-space? Well, k-space will first, you know, we go out in k-space, you know, in the x and y direction, and then we read the line. Okay. So this is our k x of t as a function of time. Okay. All right. So then we go negative in k-space, in kx. I'm just talking about kx right now. So we go in kx negative. And then we go from being negative all the way to being positive. So from this side of x k-space all the way to this side. Okay. I'm going to call the middle when we cross the center of k-space. I'm going to call that the time, this time that we cross, I'm going to call it TE. This is an important parameter, by the way, in MRI, TE. It's when you cross in the readout the center of k-space. That's what it is. I'm going to call it time t equals TE. It's also called echo time. Why it's called an echo? We'll go over it, but it will kind of make sense. Okay. So kx is really gamma over 2 pi gx, right? But at what time? Well, it's a time t minus te, right? Like, because we cross 0, kx equals 0. We cross at te, right? So this is how can I describe it? Does that make sense? Because normally we, yeah, does that make sense? Okay. So this is kx is a function of time. Yeah, I mean it's exactly what it was. It was the well, for the readout part. For this part, it is gx t minus t. Okay, just for the readout part. The important part where we collect data. Okay, so it changes linearly, and it goes from being, you know, somewhat negative, and at t equals t, it goes to 0, and then at the end it becomes positive. Now what I'm going to do is I'm going to try to represent t as a function of k, and if I do that, t would be equal to kx over gamma over 2 pi gx plus t. Okay, this is just inverting things. Okay, I haven't really done anything here. So now I'm going to look at this decay component, E minus T over T2. Now this analysis is very important. It will help you also in the homework that Ekin is going to solve tomorrow for the excitation case space, because it's very similar. Okay, but this trick of representing K as a, going from K as a function of T to T as a function of K is a really nice trick. So now I can represent E to the minus T over T2 as a function of K. And if I just substitute this here, then I would get E minus T over T2 times E minus Kx over gamma over 2 pi Gx times T2. Okay? So there's kind of two components, one that doesn't depend on K space, and one that is a function of K space. Okay. Now, as our signal decays, so when I mapped now my signal into K space, it looks like this, right? This is K space. This is Kx. And I start high, and then I start decaying till I reach the center, right? Till I reach the center. And then, it keeps on decaying. But the value at this point is E minus TE over T2. That's the value over here. Because when Kx equals 0, this equals 1. So this is the value for this part. So this part really represents the weighting of the signal, because really the image that we get is really influenced, its amplitude is influenced significantly from the DC value. And the DC value is at the center of K space. So that would create weighting of the image. Now, what about the K space dependent part? This thing. Okay, let's go over that. So there's really two effects. First of all, there's a signal loss by E to the minus T over T2. And this is effectively what we call T2 weighting. This is desired. Okay, this is desired. But the other thing is that our signal that was supposed to be constant, it was supposed to, like we always assumed, yeah, I mean, it's weighted by T2, but like we assume that it's constant, but no, it's actually weighted by some function, by some exponential. That weighting is really an apodization of K space. It's called apodization. I mean, I don't know, do you know the word apodization? I only heard about it in Dwight's class, but that's the word. But pretty much is a weighting of K space. So it's a multiplication of K space by this function. What is a multiplication in the frequency domain? How's that affecting the image?
Convolution.
It's a convolution. Convolution with what? The Fourier transform of this thing. Well, what will actually happen is that this convolution, the Fourier transform of this, has some wide kernel, like has some width to it, and that would cause blurring of the image. But you will notice that this blurring only occurs in the readout direction, only in X, because the weighting is only applied in X. The next line is going to be exactly weighted by exactly the same thing. So the weighting only happens in X. It's not applied in, it's not in KY. It's the same weighting in KY, in the direction of Y, right? So it's the same X for every Y. Because when we repeat the experiment, we excite again. And we go and read a different line. So the weighting only happens during this time. And it's exactly the same weighting, for here and for here and for here and for here. So it's the same. It's only in one direction. So the blurring will be only in one direction. Usually this blurring is just a minor effect. It's very tiny because the time that we do a readout is very short. What is usually very long is the time from here to here. This time is long, but the readout is shorter. Now, I didn't draw this to scale, but this is usually, you know, could be maybe 20 milliseconds or so. And this one is like 2 milliseconds, you know. So during 20 millisecond, you know, it can actually decay quite a bit. The waiting over 2 millisecond is not much. Okay, so it's very, very minor effect. And you can see that it can be reduced by increasing GX, because when GX is larger, then the whole thing, the whole effect will be smaller. If this is large, then the whole thing is small, and so the effect is small. Okay. So here's the situation. Look at, here's a decay of T2 with 20 milliseconds. This is a 10 milliseconds, so you know it decayed by that much. This is with T2 5 milliseconds, so it decays significantly, right? Very fast. And so if you actually think, what is the Poinsett function or the Fourier transform of this? The Fourier transform of this, for the blue curve, it's relatively sharp and high, but this, because it decays, it's lower and wider. So lower means less intensity, T2 weighting, and wider, that means blurring. And so this is just a simulation of, you know, different species that I image and simulated these decays. And you can kind of see that something with a T2 of 100 millisecond would be very bright compared to a T2 of 20 milliseconds. And 5 millisecond is going to be much darker. Now it's hard to see here any blurring because it's very subtle. Okay, the blurring is very subtle. Like you see the width of this and the width of this. Yeah, it's a little bit wider, but not that much. And you can kind of see a little bit more ringing, I think, here, and a little bit more blurring, but it's difficult to see. I can also look at the cross section, and maybe in the cross section you could kind of maybe imagine this being a little bit wider than this and this. Okay. So you get signal loss and the podization that's caused by this blurring. Okay. Beautiful. Okay. All right, so that was T2. That's it. You know what the effect of T2? It's weighting. How much weighting? Well, it depends how much time goes from the excitation to the echo time, to the middle of where you cross K-space. And then how much blurring occurs? Well, you know, it depends of, you know, how long is your readout, of course, and how strong is your gradient. If the gradient is very strong, the readout is short because you traverse K-space very quickly. And so you're not going to get a lot of blurring. Okay. And the blurring is only in 1D. It's only in the readout. There's no blurring in the phasing co-direction. Okay. So let's move to, what did we say very important? How important is this?
Extremely important.
I said very, I didn't say extremely, very important. Very important. Okay, so far we assumed B0 is really constant. It's like uniform everywhere in space, except when you apply a gradient, right? It's uniform. But B0 actually varies due to several reasons. First of all, the main field is actually we try to make it homogeneous, but it will have variation of about 1 ppm, 1 parts per million. So, you know, a 3 Tesla we're talking about what's the frequency of 3 Tesla is 127 megahertz. So 1 ppm would be 127 hertz. Okay, so there is variation, right? And it's not insignificant. It's something measurable. All right. The other thing is the object magnetic susceptibility. We said that when you put an object inside the magnetic field, it creates magnetization due to susceptibility differences. And that is actually object dependent. And that is the main problem. This is usually not a problem. This is really the big problem. And the other one, of course, is chemical shift. That's another inhomogeneity that is depending on species. For example, lipids and water tissue, they'll have different frequencies. Also, lungs, have air and all sorts of stuff. Actually, not forget about that. Forget what I said about the lungs. But chemical shift is different species. Okay. Let's talk about the main magnetic field. So the magnet is designed to be very homogeneous over a spherical volume of usually 40 centimeter diameter. Okay, that's usually the case because most people, are, I mean, it's very hard to create more. The bore itself is usually 60 centimeter. So 40 centimeters is pretty remarkable. Our scanner actually has 70 centimeter bore, so it might actually be homogeneous over 50 centimeter. Typical number, if you just make the magnet, it's going to be homogeneous up to 10 to 100 ppm. Okay, so homogeneous, but not that homogeneous. And then technicians will go and they'll try to shim it. They'll put pieces of metal in certain locations such that the field become more homogeneous to correct small deviations. Okay, to put it at 1 ppm. And again, generally, it's not a limitation. Now, we're lucky to see an installation of a scanner. So let me show you actually how they shim these passive, it's called passive shimming, where they put these pieces of metal inside the magnet. So they have this all wrenched, like whole apparatus that they use in order to calibrate the scanner and make it more homogeneous. There's these slots over here that you put rods with pieces of metal in them in different positions and with different values such that you can create this inhomogeneity that corrects the inhomogeneity of the scanner. Okay, that's the idea. Okay. Now to push these rods in and all that stuff, that's actually difficult. So what they do first is they have this device. This is the device that it's made out of. Actually, there's small NMR receivers along an arc. Each one of these is small MRI receivers. There's a small tube and there's a coil, RF coil next to them. And basically what they do is they put that thing, you see this arc? They put it inside the magnet and then they excite and receive and measure the frequency. So they use actually NMR as a magnetometer to really measure the field, right? And so what they do is they map the field by putting this here. You see NMR, magnetic field camera, it's called, and this is 32 channels. And then they go and rotate it and map the field over a sphere. And so this is kind of the map that they have. This is the front to bottom part, and this is the back to top part of the scanner, and you kind of see the field variations that they are. And then they have software that they'll go and go like, okay, so if this is the distribution, you want to make it more homogeneous, you need to put metal in rod 3, in section 5 of rod 3, and you have to add this metal in section 6 of rod 10, and so on and so forth in order to make it homogeneous. So you can kind of see now more that these are the slots where they put these rods. Okay. And now you can also see the field camera over here. This rotates the field camera so to make measurements. And this helps them pull out rods and put them back in because the rods are magnetic and the scanner is on, right? So not easy. You have to be very careful. This is a rod that you put inside these slots. And you could kind of see there's pieces of metal here with different, here there's no pieces of metal, here there is a piece of metal, here's a lot of pieces of metal, here's heavier pieces of metal. And there's tons of them over here on the table that they go and pick them up. You type this one and put it here in this slot, and the slots are numbered and the rod are numbered too. Okay, that's how they do it.
Hey, Mickey,
And I'll show you, yeah,
these pieces of metal are not ferromagnetic
they are,
and they left.
because they're supposed to change the field a lot.
And they left them sitting on the table there?
Oh, this is outside of the scanner. This is outside of the magnet room. Like this is
Oh, outside of the room. Okay, got it.
Yeah. This was just a picture I took, just to show you the rods. I wouldn't get close to the magnet with these things because they just fly in.
I would
You know.
think, yeah.
Like there's no tomorrow. I'm going to show you a video of this is Miguel, and this is Miguel. These are the two Miguels that are the field engineers. And I'll show you a video of how they pull in this thing. Take a look. You see now they have this motor, or I don't know if it's a motor, or yeah, I think it's a motor that goes and pulls this rod out because it's really stuck inside. And it's a pretty serious safety concern and you have to be very careful. So they pull this thing out. It's pretty tedious work, to do this over and over again, measure and then change this and then put it back in until it converges, So definitely an interesting problem. Okay, so this is how they shim. It's called passive shimming of the magnetic field. All right, pretty cool, huh? I'm so happy that we were able to document that. I said when I took these videos, like, this is for my class. Don't worry, I'm going to take pictures. And so yeah, it's happened. I can't imagine, and this is 2 years later. So super excited that I got these videos. All right. So what about object susceptibility? So most biological objects perturb the field. And so basically there's some delta BZ because of tissue. And that is approximately, some zeta times B0 of free space. So whatever B0 is, then because you apply, because you put some material here, there is magnetic susceptibility constants that multiplies and changes basically the field. The zeta is it's called magnetic susceptibility. And as it turns out, the Larmor frequency is lower in tissue than it's in the air. So the fact that you put your body inside a 3 Tesla, the field inside your body will be lower than 3 Tesla, just because you're inside and because you're mostly water. Okay, so you're gonna slightly reduce the field inside your body because you just put it in it. So magnetic susceptibility of water is about minus 9.05 ppm with respect to free space. The magnetic susceptibility of air is 0.36 ppm with respect to free space. So it's higher. It's a little bit paramagnetic, it's called, because oxygen is paramagnetic. Okay, so there's about almost 9.5 ppm between water and air difference, right? So it's pretty big. Now, the fact that I put, let's say, a cylinder or a sphere of water inside air in a magnetic field, it will create, as you move up, if this is the direction of the magnetic field, this is the direction of B0 over here, then the field inside the sphere is going to be different, but it actually also going to affect the field outside of that sphere. And delta BZ for that sphere is going to be actually some function of the radius. It kind of looks like this. Decays with r to the third, but above it is going to be higher. On the sides is going to be lower, and below it's going to be higher. And this is just the component of the field in the z direction, because we really don't care about the component of the field in the other directions. They don't really contribute anything. Okay, so the fact that I put a sphere inside the magnet, it creates these perturbations. So there are really complex behaviors at the boundaries of different tissues and different materials. And that depends on the change in susceptibility and also depends on the geometry. So typical delta B0 in the body is about plus minus 3 ppm. So it's a susceptibility range of about minus 12 to minus 6, something like this, inside the body. There's a beautiful paper by John Skenk, and I'm going to post it on the class website. Aiken, let's post it on the class website. It was posted in previous years. Okay. It's a beautiful, and that paper says it's called The Role of Magnetic Susceptibility in MRI. It's amazing review paper. It's one of the best papers I've ever read. It's just beautiful, so comprehensive. And so you can see that different geometries will create different susceptibility effects. So if this is the z direction, which is the direction of B0, and this is some x direction, if I put a cylinder that's oriented in the z direction, then that cylinder will have a shift in its magnetic field, but only inside the cylinder. And it's really not going to affect anything outside. But if you have a sphere, you're going to see a shift inside the sphere, but now it's also going to perturb the field outside of that sphere. And then if I have a cylinder that is actually oriented perpendicular to the field, not along the field, Rebecca, you're going to do these type of experiments, right, with bottles. So this is what we were talking about. This is why I'm emphasizing this. So if you put a cylinder perpendicular to the field, then it will actually create effects outside and will perturb the field. Okay. Now there are some problem areas, in particular in the brain above the sinuses. The sinuses is air. Air is about 9.5 ppm away from water. So that susceptibility difference is big. And air, there's these air pockets in the sinuses, and the brain is close to the sinuses. So if we actually map the field inside a slice of the brain, you see that the field here is higher than the field in the center and the field in the back. And this is kind of the distribution of it. And so the area really close to the sinuses is a real problem in terms of susceptibility. So there's a big field variation. So the brain above the sinuses and the auditory canals are a problem. Also auditory canals, they go inside and they create a problem. Heart is surrounded by lungs. Lungs, turns out, have air in them. Right? So that creates a huge susceptibility problem to the, and then abdomen also has lots of different type of tissue, but also have bowels. And bowels, guess what? You know, sometimes when you eat a lot of beans, there's something created in your bowels called gases. And so they move around and create susceptibility artifacts, okay, in the bowels. Okay, so that could also be an issue. So abdomen, heart, and brain are problem areas.
Hey, Nikki.
Yep.
On that map, so is that a susceptibility map?
No, this is a, Well, what am I doing? Well, hold on. This is a frequency map. It's a field map. It's what is the field of the scanner within the slice of the brain.
And it's not
Okay,
related
so
to
it's supposed to-
it's not related
if
to
it was you-
susceptibility map.
It's a little bit related, but it's not a susceptibility map. It's
Okay.
actually the map. I mean, it could be a result of actually the scanner, the magnet inhomogeneity. It could be a result of many things, right? So it's
Okay.
just a map of the frequency. So spins over here resonate at 100 hertz off resonance. Spins here resonate on resonance. Spins here resonate at, I don't know, 30 hertz off resonance plus, and so on and so forth. Okay.
Okay.
Now, there are macroscopic effects to susceptibility. For example, if you put a metal inside an MRI, I mean, it will create huge patterns. So this is X position, this is Z position, and this is a field map. You see huge artifacts because of metal. This is a cross section of these artifacts, and those effects are so huge that they not only affect the imaging, but they also affect the excitation. Because if you try to excite actually a slice, because of the metal, areas that are far away are going to resonate at very different frequencies. So you might excite, other different parts. So you're thinking you're exciting a slice, but now your slice are crooked. You're not actually, you're applying a gradient in this direction and trying to excite a slice, but the metal distorts it and it creates very weird slices. This is a photograph or an image of a leg that was acquired on a 3 Tesla MRI by Anita. Anita acquired it a week and a half ago. And this subject has implants, metal implants in their tibia, because they did something stupid and broke their tibia, and they had to go through a surgery and had metal implants. This is titanium. Okay, so titanium is non-magnetic. Its susceptibility is not very high with respect to metals, but it's still high enough. And there's a lot of artifacts you can see here, definitely darkening and brightening and all sorts of stuff, because the slice is not very well selected. And also there's all sorts of effects that we'll be able to analyze. So this is a real problem for me and for people that have metal implants in them. Okay, so when they want to do MRI. Now, the beauty about this is because it's titanium, that it's really only bounded to kind of this area of where the metal implant is and not far away from it. But if this was stainless steel, you would see a black hole. If it was stainless steel, it was so bad it would have been. That's why I insisted on titanium. If you get metal implants, insist on titanium, huh?
Could you even go in with steel?
With stainless steel, yeah, no problem.
Oh,
It's
stainless.
non-magnetic.
Well, okay.
Now, the beauty about this thing is that if, let's say, this patient or subject hurts their ankle at some point in the future, you'll still be able to see the ankle in an MRI. Okay, so it's not a problem. But if this was stainless steel, there's no way. That's from a beautiful paper. So the susceptibility of titanium is 182. Stainless steel is 3,520. It's like really big. It's huge. It's non-magnetic, but it's huge susceptibility difference. Titanium is big, but it's not, it's not even close to this. So these are metal implants. This is metal artifacts. This is from a paper by Brian Hargreaves of a paper called CMAC that tries to mitigate with metal artifacts. And it shows these metal artifacts, and then it shows a technique that using fancy pulse sequence and processing, you can actually image next to metal and be able to, image this knee, even though it was, had screws in it. This could be a phenomenal project, either implementing the method or reviewing methods for metal artifact reduction in MRI. That would be a good project. So, you know, if you resonate with this project, you know, you could actually implement a technique like this, you know, on the scanner, if you wanted to. It's actually not that hard, either on the aspect scanner or even on the GE scanner. Okay. All right. It's 5:10. I already 10 minutes past. I'll just say that there's beyond macroscopic effect, there's also microscopic effects. Because, for example, in the lung, you have these nodules, right? Like a small air nodules inside, and there's also water and nodules and water. So it's really a mix of many, many different tissues in a very small area. And so there is going to be microscopic effects of susceptibility, not large effect like you've seen with the metal or, you know, things like that. So we're going to talk about that. And actually, the effect of the susceptibility has a lot of information about the microstructure of tissue. So people investigate that a lot. But you can see that if water is minus 9.05 ppm in terms of susceptibility, air is 0.36, lungs is about -6, because it's a mix of air and tissue together. And it's also very broad. So because of, you know, it's not very focused. So it's very broad spectrum, right? Of course, susceptibility translates into frequency, right? So you'll have a broad spectrum of frequency over there. And we'll talk about that. We'll talk about that Thursday. And on Thursday, we're gonna talk about the effects of the susceptibility or these field homogeneities on the imaging and what happens. We're gonna come up with something called T2 star, and I'll play you this song that I didn't get to today. All right, so I apologize for the song. Sorry about stealing 12 minutes out of your time. Have a nice day, and I'll see you on Thursday. Bye-bye.